Hello and welcome to WBS 5. This module may seem a little bit more intimidating because it does use statistical techniques, but I want you to keep in mind the big picture. What is it that we're trying to achieve in WBS 5? What we're trying to do is calculate the probability of finishing the project by a particular time. Now, we didn't have to worry about that in WBS 4 because in WBS 4 we had our times given to us. We assumed that each task had a fixed duration. So in that sense, the critical path method is a deterministic method. It assumes that the times are a given and they're not going to vary. But in real life, that almost never happens. So the PERT method, Program Evaluation and Review Technique, use statistical techniques to calculate the probability of completing a schedule by a certain duration. And the reason those probabilities are there is simply because you use 3-point estimates for each task. Instead of the duration being given to you, you estimate the best case, the worst case, and the most likely scenario for each task on the critical path. Now, since you take a weighted average of best case, worst case, and most likely, it's a special kind of weighted average, then you can take the task duration average and you can match that to the normal curve in order to calculate probabilities, because you know, for example, the midpoint of the normal curve, there's a 50% probability of finding something in the midpoint of a normal curve. Unfortunately, half of all people are below average, half are above average. The 50% mark is in the center of the normal curve. All right, before we get too complicated, though, when we calculate statistics and probability, let's see how simple it is to determine the probability of achieving a certain schedule date simply by using 3-point estimates, a weighted average of 3-point estimates for each duration. So let's take a look. So in PERT, we assume each activity has a range that follows the beta distribution. Now, right away, you might say, what's the beta distribution? The beta distribution is a special type of weighted average. You're weighting the most likely time estimate higher than the other estimates. So you have a best case estimate or an optimistic estimate, a pessimistic estimate, and then you multiply the most likely estimate by 4. It works like this: optimistic plus 4 times most likely plus pessimistic divided by 6. So that weighted average is based on the beta distribution. You don't need to know that other than be familiar with the term, but that's where it comes from. Best case, 4 times most likely, plus worst case divided by 6. So if you can do that for every activity on the critical path, then once you calculate the average, and again, what you found with best case, worst case, most likely, then you have 4 times most likely, and that's all divided by 6. That's a weighted average. Once you have a weighted average estimate of every task on the critical path, you can also calculate the variance, the range of possible times in which each activity may occur. You can also find the standard deviation, and the standard deviation is a standard measure of how wide your normal curve is. And also it measures the distance from the midpoint, how many standard deviations away from the midpoint. So what we've done here is taken time estimates for the durations of activities, created weighted averages. We can calculate variances, calculate standard deviation, and if you have all of those figures, you can also use that to calculate probability. And here's how we do it. Okay, first of all, the project average is known as the TE. That is the estimated time. The project average is derived by taking each of the weighted average estimates of all activities on the critical path, and it produces a normal curve. But each of the activities on the critical path are estimated using the best case plus 4 times most likely plus worst case divided by 6. And that's the beta distribution in A. So you use the weighted average or the beta distribution for every activity on the critical path. Once you find all of those averages, it becomes the project average when you add up all of those activities on the critical path. Here's the formula. The weighted average activity time optimistic, pessimistic, most likely. So of all of our talk of statistics, this formula is very simple. You could work it out with a pencil and a piece of paper. You may not even need a calculator in a lot of cases. Now you find the standard deviation by taking pessimistic minus optimistic over 6, or B minus A over 6. That's pretty simple. Now in statistics, the standard deviation is the square root of the variance. So squaring this term produces the variance. If B minus A over 6 is the standard deviation, the variance is B minus A over 6 squared, simply because the standard deviation is the square root of the variance. So the standard deviation for the project, you add up all the variances of every activity on the critical path. That's what this sideways M is. That means the sum of all variances on the critical path. You take the square root of that, and that gives you your project standard deviation. Okay? So just to review, we find this for every activity on the critical path. We take B minus A over 6 squared. That's the variance of each of those activities on the critical path. And the B minus A is pessimistic minus optimistic over 6 squared. You sum them all up and take the square root of it, and then that's the project standard deviation. Why is that important? Because the project standard deviation will be in a unit of time. So if you know the project average completion date, which is the sum of the averages of all activities on the critical path, and you know the standard deviation, and standard deviations are on units of time, you could calculate the probability of completing the project by a specific time. Here's an example of activity times and variances that you'll be given in problems in this text. You're given, instead of the time for each activity, you're given the optimistic, pessimistic, most likely. Here the average is calculated for you, and then the variance is calculated for you. The average is simply A plus 4 times M plus B divided by 6. That's the weighted average. And then the variance is B minus A over 6 squared. Okay, and this gives you the activities, but you don't need to add up all of those variances. You just need to find those that are on the critical path. So when you're completing a PERT network analysis, you first take this, you find the TE for every activity, you create a network diagram, you determine the critical path, then you sum the variances of every activity on the critical path to find the project standard deviation, and you sum the TE for all activities on the critical path to give you the project average. And then when you are given a unit of time, let's say your boss says, I want you to take 1 week off of the schedule. If you know the project standard deviation, you can ask yourself, well, if I have to shorten this project by 1 week, how many standard deviations is that? And if you can put that in terms of number of standard deviations, then you can calculate the probability of actually completing it. The z-score, and most of us don't walk around with a z-table in our pocket, but the z-score is simply number of standard deviations. Okay, so the scheduled project duration minus the TE, which is the sum of the averaged estimates for every activity on the critical path, divided by the project standard deviation. This gives you number of standard deviations, which is z, and then you can look that up on the z-table. Here's a hypothetical network. We found the critical path. Here we're doing it on activity on node. All right, so if the probability, probability is completed before the scheduled time of 67 units. Okay, so let's say if the TE in this case, which we've determined this, is 64 days, what's the probability of completing it in 67 days? So we take 67 minus 64, divide it by the project standard deviation. That's plus 0.5 standard deviations, or z equals plus 0.5. Look that up on a z-table. The probability is 69%. Rule of thumb is the midpoint of the normal curve is always 50%. So that also tells you something interesting, that if you sum up all the average estimates, the probability of achieving that schedule is only 50%, which is not big. So when you create estimates like that, and your boss tries to make the schedule shorter, you can say right away, hey, there's only 50-50 chance of achieving it by this given time. So here we've added days to the average estimate and notice that the probability increased from 50% to 69%. What happens if we try to reduce the project? If 64 days, and we see this by the network diagram, was the average or the TE for the whole project, 60 minus 64, that's reducing by 4 days. That's minus 0.67 standard deviations. Look that up on the z-table. The probability is only 26%. So if you left it at 64, you'd have a 50-50 chance. You remove almost 1 standard deviation, now you have only a 26% chance. And this shows the z-table and probability. Notice we had plus 0.5 standard deviations. That's between 0.4 and 0.6, so you'll see it comes between 0.655 and 0.726. So calculated exactly, it's 0.69. Minus 0.67, that's between minus 6 and minus 8. It's somewhere between 27 and 21. We see it turned out to be 26%. Okay, so this can be a little bit daunting, as I mentioned, but don't lose track of the big picture. You're trying to take estimates for each of the activities on the critical path, find out which ones they are, find the project average and the standard deviation, so you can link units of time into project standard deviations. So if someone wants you to add time or reduce time, and usually it's reduce time, you can ask yourself how many standard deviations is that, compare it to the normal curve, and you'll arrive at the probability of actually finishing the project by that given time. So I'm going to post the slides that I give in the Eagle Vision session this week that have a little bit more detail and give you some additional cases. But if you always remember, don't lose track of the forest for the trees, I think you'll do fine in WBS 5. So let's get started on WBS 5. We'll see you in the discussion threads this week, and let me know your questions or issues.